Okay, nice. So we are going to be going over Note 11 in CS70. This one is about infinity, countability, and a little bit about computability. It's mostly the first two, I think. But first thing we're going to go over is bijections. We're going to revisit them. So here are some pictures and their definitions. So this represents something that is one-to-one. And that basically means every x maps to a unique y, such that if f of x is equal to f of y, then x must be equal to y. Like here. Onto means that every y gets hit. So I think that's pretty much how they say it here. So for all y, there exists some x such that that x maps to the y. Okay, and then a bijection is both one-to-one and onto, as we have discussed. Okay, and I guess just to reiterate, we have these two kind of spaces, A and B, and F takes us from A to B. Next, we're going to talk about cardinality. So how do we check to see if two sets have the same size? Well, we find a one-to-one mapping between elements in the set, or we find a bijection, right? So first question is, are there more natural numbers than positive integers? And we're going to use this above approach to demonstrate that there are in fact the same amount of natural numbers as there are positive integers. What is f? So if a, say a is the space of natural numbers and we want to map to the space of positive integers, f of x would just be x plus 1, right? So our input is 0, x plus 1 brings us to 1. Our input is 1, x plus 1 brings us to 2. Okay, so is f onto? Yes, it's onto because every x maps to some y, and then is it one-to-one? Well, as we can see, all y have some x. So therefore, because this is one-to-one and onto, there's a bijection. And so the set of natural numbers is the same size of the set as the set of positive integers. So I'm going to write that down, and actually I think something that my GSI said is that it's good to know, just be able to recall off the top of your head which sets are the same size, or sorry, are countable. And we'll discuss what it means to be countable in a little bit. So let me just, how should I do this? I'm going to pause for a second. Okay, so moving on to the next part, are there more natural numbers than 2 times the set of natural numbers? So we're going to pretty much repeat the process. Set of natural numbers, just 0 through 5, and then here we have 0 through 10. F would just be 2x, right? And then I guess our inverse function would be y over 2. And we can see from this picture that f is onto and f is one-to-one. And it's a little easier to see with this, but we can also show that there is a bijection between the set of natural numbers and the set of integers. And our function f is going to be this, where if we have an even number, then we're just going to divide our x by 2, our number in the natural number divided by 2, and then if the number in the natural numbers is odd, then we're going to add 1 divided by 2 and then put a negative in front of it. So if you just want to like visualize it, it's just kind of like a natural, so for the natural number line, it's just going, it's increasing, and then for the negative numbers, you know, it's just going to 0, it's going to 1, -1, it's going up to -2, 2, and so on, kind of like flipping or zigzagging, I guess, like yeah, zigzagging in a way that like expands out, but anyways, that's not really important. So let's see, I guess this is just the proof that it takes this form. So again, we're going to show that the set of natural numbers and the set of integers is one-to-one, and something that we defined up there is that if 2 inputs are different, then their outputs are different, and this is just a property of something being one-to-one. So let me just, okay, yeah. So we're just kind of taking this function. In the even case, you know, we have two different inputs, x and y, then we yield two different outputs. But if we say that x is equal to y, then their outputs must be equal, and so x and y must be equal. So that proves the even case. And then for the odd case, let's say we have two different inputs, x and y. That means we should have two different outputs. But if it's the case that the outputs are the same, then it must be the case that the inputs are the same. So because f of x is equal to f of y in both the odd and the even cases, then it must be the case that x is equal to y. And therefore we've demonstrated this property, which shows that this is 1-to-1. Okay, now we're going to demonstrate the onto proof, which is pretty simple. We're just kind of going to use the function. And so onto again just means that every y is hit. So basically, if we have a y, we should be able to trace it back to some x, right? So we can just say that f of 2y is equal to y. And what this is saying is that we have our output. We're going to kind of like undo the output. And that means that we should have some input. So then when we throw the input back in, we should get the original y. And this is just demonstrating it for the even and then the odd case. Okay, and as you can see, these are just kind of like the same equations as up here. We're just solving for y. It's like, say we set y equal to x over 2. We're just going to solve for, or I guess x in this case, to put into the x position in this function. So hopefully that makes sense. And now we're going to go over what it means to be countable, which we sort of talked or hinted at earlier. So a set S is countable if there exists a bijection between it and the set of natural numbers, or a subset of the natural numbers. And I mean, I think that sort of makes sense. That's kind of what the set of natural numbers is, like the set of naturally countable numbers, I guess. So if we can map our set S to those numbers, then we know we can count it. And as you've kind of seen, we've sort of been comparing everything to the set of natural numbers so far. Okay, and now we're going to see if there is a bijection between the set of natural numbers and between the set of rational numbers. So we're just going to recall the definition of a rational number. A rational number is a number that can be expressed by a divided by b, such that a is an integer and b is also an integer, as long as b is not equal to 0. And then another way we can show bijection is to show that the set of natural numbers, or actually this is the general case. I did not mean to do that. Okay. So in the general case, if we want to show a bijection between two sets, we want to say that the size of set A is less than or equal to the size of set B, and then also the size of set B is less than or equal to the size of set A. And the only way for those two statements to simultaneously be true is if the size of A is equal to the size of B. And therefore we can trace, we can create a bijection between the two sets. So it's clear that the set of natural numbers is less than or equal to the set of rational numbers, because we can express all natural numbers in this form, like two integers where one is divided by the other. But how can we show that the set of rational numbers is less than or equal to the set of natural numbers? So we're going to use this cool image here, and the x-axis is going to represent values for the numerator, or a values, and then the y-axis is going to represent values for the denominator. So as we can see from here, the kind of like the set of numbers that we're generating is going to be z times z, right? Because we have all possible z's in the x direction and then all possible z's in the y direction. And we know that for the set of natural numbers, And yeah, that's expressed here. That's what we're going to talk about. Or sorry, for the set of rational numbers, some of these don't exactly work. For example, when y is equal to 0, that can't be a rational number, because the y-axis represents values that we would put in the denominator of the expression that is supposed to represent a rational number. Again, it's like a divided by b, such that b is not equal to 0 and a and b are integers. So b can't be 0, y can't be 0. And then also, there's ratios. So if we go to the point 2, 8, we're just going to get the same number. It's 1, 4. But we can also see that we can create a mapping between every natural number and every possible pair in this setup, right? So if we can create a mapping between every natural number and every number in z by z, that means that z by z is countable. And because Q is the set of rational numbers is a subset of z by z, which is countable, then the set of rational numbers is also countable. Okay? And is there a bijection between all bits and strings? It's not necessarily apparent. Maybe I should take that out. I think I said that just because we sort of represent decimals, or strings, or what is it? Bit strings are base 2 representation of natural numbers, right? Which natural numbers are base 10, bit strings are base 2, but anyways, we're just going to want to show a bijection between this and the set of natural numbers, where this sort of represents all the possible combinations of zeros and ones of an unending length. And this symbol right here, I don't remember what this letter is called, but it just represents the empty set. So set of all, so yeah, we can basically just create a one-to-one mapping like we've been doing for all of the other sets. And now we're going to show that the set of all polynomials with natural number coefficients is also countable. So we're going to sort of use this argument up here, and we're going to expand it out to now say that the set of all ternary strings, or strings that can be made with 0, 1, and 2, is countable. I mean, it sort of follows from the same logic. So this, you can just create a one-to-one mapping. So we're going to have our polynomial. It's going to have natural number coefficients. We can just represent this as a list, and then we can represent each coefficient in its base 2 form, or its bit string form. Then from there, we can simply put 2's in between each coefficient. And each coefficient corresponds to, for example, this would be A5, A4, A3, A2, A1. And so they all correspond to, we have A5, A4, A3, A2 in this case is 0, A1 is 4, and then A0 would be 6. And from this point, we can determine, I guess we don't actually have, let's see, it doesn't seem like we have included the coefficient A2, so we wouldn't necessarily know what monomial it would be multiplying, but we can still sort of represent it in this way, where we just separate the coefficients by 2's. So yeah, hopefully that makes sense. Okay, and we're going to move on to, I don't really need to close this, so Cantor's diagonalization. So we want to see if the set of real numbers is countable. And we're actually just going to confine ourselves to the set of real numbers between 0 and 1. And so let's see. Yeah, so I think the real numbers encapsulate both the rational numbers and the irrational numbers. Where an irrational number is something with an unending decimal that is an unending decimal and cannot be expressed as a fraction, as rational numbers can be. So what we're going to do is sort of just try to create upfront a one-to-one mapping between our set of natural numbers and then just our set of real numbers that are between 0 and 1. So we're just going to have these huge decimal points, and then we're just going to, or decimals, and then we're going to map it to natural numbers, right? It seems like we can do that just at face value, but let's say we construct a number r from the diagonals of all of the numbers on this right-hand side. So it would be, if we follow the circles, it would be 0.5479. And then let's say we apply some function to it. In this case, we're going to add 2 mod 10 to each digit. So yeah, we're basically just going to do that. And then if we assume that there is a natural number that maps to S, well, let's say that natural number is n, right? It's somewhere down here. And that number maps to this value right here. But, or sorry, I think it should be, let's say there is a number that maps to R. Right, and, or let's see. Actually, I guess it could be either way. No, let's just say R for now, okay? Or sorry, S. Okay, let's say S. So the nth natural number is going to map to our real number S, which is this. But if we remember, the way that we obtained S is by adding 2 mod 10 to every digit along the diagonal. And if you think about it, it's going to hit every number in the set of real numbers, right? So if we do that, then that must mean that to the nth digit of n, or sorry, of S, should have also been flipped. And so that means, just by definition, that it can't be equal to S. And so, or I guess it would be the nth plus 1th digit? Yeah, because 0, this is, if we say this is 0, this is the 1th digit, 1, this is the 2nd digit. So it would be off by 2 mod 10, and yeah, so basically just by this logic, we will not be able to find this number, or yeah, this number in our set of real numbers. So let's see. There's also the case where we can have numbers with infinitely repeating decimal places of this form can just equal their rounded version. And so if we had chosen f of n to be just 1 mod 10 or negative 1 mod 10, then we would have run into an error. So, you know, if we offset it by 2, then we sort of circumvent that issue. So let's see, if we apply this diagonalization to Q, it fails because upon adding 2 mod 10 to any decimal, it's unlikely that that number will remain rational. Okay. So next we're going to go on to the Cantor set. So I feel like visually is the best way to think about it. So we're just going to start off with some number that is like, it's like 0 through 1, right? And then we're going to break it up into thirds, and we're going to remove the middle third. And then for each of those thirds, we're just going to recursively, inductively, however you want to think about it, do the same process. So we're going to take this third, take out a third of it, and then keep our remaining thirds on the end. And if you want to calculate the size of these pieces, you can take this limit, and this limit says that we approach 0. However, we know, even though we're technically dividing something over and over again, we know that the Cantor set is both non-empty and uncountable. So how are we going to show that it's uncountable? So let's see. We can have these strings to represent the divisions. So on the first iteration, again, we're going to say the string, I don't know if we specified. But we're going to have, yeah, so we have this range from 0 to 1, right? So we're going to break this up into thirds such that the first or the second third is going to be removed. So it's anything from, let's see, 0.1 repeating. So let's see. Actually, I guess this technically represents the second iteration, because right here we have a third, right? So with that third, we're going to keep this middle part, or actually I guess we're going to take the middle part, and then we're going to keep everything from 0 up to the very end, and then we're going to keep everything again from here, 0.2 up to like as far as that goes. And you know, on the second iteration, we're basically going to do the same thing. We just move the decimal place over. And so what we're saying is that the Cantor set has a ternary set consisting of only 1s and 2s, which means you could create a bijection between this and this, and we know this is uncountable. So did I actually say that? I think I might have messed up, actually. Where it's an image, let's see, give me 1 second. Sorry, so yeah, what I said earlier was right. So this is actually what I wrote here is incorrect. This is countable. This represents the set of finite binary strings, and that's countable. But what we're saying here is that there's a bijection, or not, sorry, there's not a bijection. There's a mapping of all of these integers, or real numbers. So, sorry, yeah, that's basically what it is. All of these decimals can be mapped to some real number between 0 and 1, right? And we know that that set of real numbers is uncountable. So therefore, those decimals are uncountable, and this set is uncountable. So let's see. Again, those decimals were numbers between 0 and 1, and they were just like all of those decimals there. So to clean this up, which means create a bijection between, I don't think it's a bijection, it's more of like a mapping, and then we know that it's math, or I think it's like that, from 0 to 1 is not countable. So yeah, okay, we're going to move on to power sets and higher orders of infinity. So first off, I was sort of lazy. I didn't actually make the letters look the way they should, but this represents the power set of S. We talked about this way back in note 0, I think, actually. So a power set is basically just all subsets of a set S. And you know, if we think about the set 3, or a set of size 3 with elements 1, 2, and 3, we can have a subset of size 0, which is just the empty set, and then we can have 3 subsets of size 1, you know, a subset of 1, a set of 2, and a set of 3, and then we can do every combination of just 2s, and then we have that one set of size 3 with all elements in it. So the formula for that is basically, I don't know why there's an n there. The power set is the size, or the size of the power set is equal to 2 times k, where k is the number of sets or elements in the set. And I mean, you can represent this as a bit string. So you know, I think they have, is there an image here? Well, yeah. So if we go back to that metaphor of, or I guess example, of a set with 3 elements, 1, 2, and 3, we can have a bit string where each place maps to, one of those elements. So the first place maps to element 1, the second place maps to element 2, and the third place maps to element 3. For each place, we can choose to either include that element or exclude that element. And that's something that hopefully we should have heard at some point. That sort of signals 2 times the number of elements, or 2 to the number of elements we have. That's the number of choices we have, or ways to create that bit string. So let's see. We're going to show that the power set of the set of natural numbers is greater than the set of natural numbers. So let's see, we can enumerate all of the natural numbers using an infinite bit string, or bit strings. So the index on the row refers to a number in the set of natural numbers, and then ones in the column mean that we include that binary string or subset, and we're going to diagonalize and obtain a number b, which is the result of flipping all the bits on the diagonal. And by construction, b must be in the set of natural numbers because b is just a bit string. And if we assume that b occurred at position n, we know that it can't be the case because we flipped all positions or all bits along the diagonal, which means that we had to have flipped the nth digit. And so therefore we can't map all subsets of n to all values in n, where n is the set of natural numbers. So that has been note 11, all about infinity and countability, and yep, that pretty much wraps up this video.